All right. Hi again, everybody. So this time it's for real. So we're going to get started with the talks now. Thank you again so much for coming. We still have a ton of pizza in the back and a ton of drinks. I have been told we are not allowed to leave leftover drinks in this room. They have to be dealt with. So please help me deal with the problem, either during or after this talk. Anyway, so our first speaker of the evening is going to be Greg Szorc. Greg is a developer productivity engineer at Airbnb. Prior to Airbnb, he was at Mozilla, where among other things, he was a contributor to the Mercurial project. So give a big round of applause for Greg. Take it away.
Cool. Is my mic on? Yes. Sweet. All right. So I guess this was already said, but that's me. One thing that wasn't said was I have a blog at gregoryszorc.com, which has a lot of information mostly about version control stuff. I am a core contributor to the Mercurial version control tool. I've been doing that for several years. Really into build systems and version control and lots of developer tooling things. So yeah, actually, before I go into the talk, I'm curious if there's anyone here who has heard of PyOxidizer before. OK. Is there anyone here who's like squarely in the, you are a Python developer camp and you came because you wanted to hear about PyOxidizer? All right. So this is actually good because I figured this is a Rust audience, so I tailored it for Rust. So before I talk about what PyOxidizer is, I want to start from my first principles here, that software is a tool empowering people to achieve a higher order goal. Furthermore, most people care that software enables them. They care little about the software itself. The major exception to this is developers, probably the people in this room. We care, or we like to think we care, about things like what language software is implemented in, even though the technical implementations usually just don't care. They don't often affect the underlying utility of a piece of software. However, lots of software forces people to care about the technical underpinnings of it. Most people, they just want something they can double click on to run. This is like your parents, your grandparents, your aunt and uncle who aren't as technically literate. They just want to download something from an app store, something like that, and click on it to run. They want an icon. So let's give some examples of this. This is how you would run software on Mac OS if you want to use Homebrew, for example. And to you and me, if we use Macs, like we're familiar with this. There's a package manager, and you install the package manager, and you run a command to install software. Sounds easy for us, harder for non-technically literate people. For Python, you may have seen this XKCD. It's pretty bad in Python. This came out several years ago, and I think things are slightly better than this, but Python is generally pretty bad. I'd say Ruby is also in the same boat here. And not to diss on the Python community or the dynamic language community that much, Rust has this problem as well. How do you install a Rust application? Cargo install. What's cargo? It's a package manager. What's a package manager? What's Rust? People, they don't want to deal with this. This is all things that we force people to deal with to run software. And I ran into this when I released PyOxidizer. It's a Rust application targeting Python users, Python application developers. And there were a handful of people who complained that I did not provide a standalone executable for PyOxidizer. Because they didn't want to go through the hassle of installing Rust up and installing a compiler, toolchain, and all that. So in summary, in meme form, yeah, people like their nice clicky icons. They don't like command line tools. And so that brings us to PyOxidizer. And the first goal of PyOxidizer is that installing and running Python software should spark joy. And the reason that Python is in square brackets there is to emphasize that the consumers of software should not have to care about what language or technologies that software uses. Again, people think of software as a tool that enables them. They don't, it shouldn't be more than that for the average user. And so how does PyOxidizer do this? It empowers Python application maintainers to distribute software with as little effort as possible. And did that work? No, it did not go through. Oops, did I miss a slide? Yeah. So essentially what PyOxidizer is a tool that's written in Rust that enables you to take a Python application and compile it down to a single file, as small as a single file executable, which then you can give to someone else and they can just install it on their machine and run it. Contrast that with the XKCD comic, which is crazy, right? And so from normal tooling perspective, like PyOxidizer is just some command line tool that you use to enable people to package Python applications. That's it. There's a lot of dark magic going on behind the scenes, however. So software distribution is a really hard problem. Giving someone else a binary that they can run on their machine is fraught with challenges. Fortunately, like a lot of people aren't exposed to this. You have if you're at a big company, you probably have a build team. If you ship software to other people who has to deal with these problems, if you're in server-side software, fortunately, usually you don't have to deal with these problems. But if you run like Linux in your server fleet and you have different versions of distributions, like you have all these problems with like libc compatibility. These problems exist on Windows with DLL hell, on Mac OS. It's all the same, different manifestations of the same problem. And so one of the things that PyOxidizer does is we have to build a special distribution of Python that is compiled with all of its dependencies from source in such a way that the binary is portable to different machines. This problem has probably consumed more of my time than writing PyOxidizer itself, because build systems are hard, and I'm making build systems do things like CPython's build system do things that it was not intended to do. But at the end of the day, what happens is that basically we produce a set of object files that you would normally get from your compiler, put those in a tarball, and then tell Rust to relink. What PyOxidizer does is it consumes the metadata for the Python distribution, figures out like, oh, you want the SSL Python extension that requires all of these libraries, these object files, all of that. PyOxidizer integrates, tells Cargo which object files to bring into the build, and then Cargo will link together a Rust application as if it was a C library or something like that. Kind of hard to explain, and if you want to know more details about how that works, you can ask me after the talk. And so, are there any questions so far? I guess I kind of briefly only talked about what PyOxidizer did. No. I am using the CPython build system, but there are a number of patches I've had to apply at build time to get it to do the things that I want. My intention is to make a lot of those upstreamed at some point. I'm not there yet. I want to kind of figure out what all I need to do first before I start sending crazy patches to Python, because I suspect they're going to be skeptical. Yeah, so when I was at Firefox, when I was at Mozilla, one of my jobs was to be a maintainer of the Firefox build system. And one of my takeaways from that was that it is often less effort to just rewrite the build system for a third-party project than to coerce that build system into doing what you want. And I hate saying that, but we realized it time after time that that was the right trade-off, because you would sink dozens of hours into working around other people's problems. I still have more. I was just a midway point for questions, but yeah. Yeah, I will get to that actually. I should probably continue. I just wanted to make sure I wasn't like completely losing the audience here. So PyOxidizer it's basically a lot of build system hackery around Cargo and Python's build system to produce a executable that contains an embedded version of Python. And at runtime, what makes PyOxidizer different from, actually I'll get to that later. But so applications built with PyOxidizer are just normal, they're normal Rust applications. There's a main function. It just so happens that that main function instantiates a Rust struct defining how to run a Python interpreter, and then it calls a run function. It's pretty simple, and the code in Rust at runtime is something like, well, there's a little bit of extra code here because there are some runtime tricks. And these are kind of low-level Python-y things. I don't know how relevant this will be to this audience, but it may be relevant if others want to explore how to do this for other languages like Ruby. So one of the nifty things that PyOxidizer does, which I believe is the first project to do this in a cross-platform way, is it actually achieves a single file executable with no external dependencies without any additional runtime tricks. So other tools in this space will do things like create a squashfs file system, or they'll create a temp directory and extract the Python standard library that's embedded as a zip file into some file system, and then they'll tell Python, hey, the modules are over here, and that's how things work. That can add a substantial runtime penalty. What PyOxidizer does is we have a custom data structure with all the Python bytecode in it, and that's just embedded in the Rust application via an include bytes. And at runtime, that data structure is parsed into, I get into this in the next slide. It's parsed into a hash map, a Rust hash map of like, here's all the modules that you have available. And then when Python's import system runs, it calls into a Python extension that's implemented in Rust. And that extension does basically the equivalent of a Rust hash map lookup. And it's like, do I have information on this module? If it does, it creates a Python type that holds a reference to the memory location, the static memory location, where the bytes for that bytecode reside. And that gets fed into the bowels of the Python interpreter and executed. And so what this means is that normally when you run a Python application, it's like statting all over the file system, trying to find all of its modules. And the number of stats it does is actually can be pretty insane. If you have like multiple directories on your sys path, it has to look in all those locations, and there's all these rules for the priorities of things. I'm going to skip this real quick and go back to it. But to give you an example of this, so what PyOxidizer does is, because it's loading all of this from memory without having to touch the file system, the overhead of starting a Python interpreter is substantially mitigated. So I also said that I'm a core contributor to the Mercurial version control tool. And a few years ago, I measured how long it took like the test harness to run. And you run on a laptop, it takes like 20 minutes to run the full Mercurial test harness. And when you start digging into where that time is spent, it turns out that Python interpreter startup overhead is actually a thing. You run it from your command line tool. You use a tool like Hyperfine, which is an amazing Rust benchmarking tool for crude benchmarking. But you run a tool like that, and it's like, oh, it's 5 seconds, 10 milliseconds, sorry, 5 or 10 milliseconds. Doesn't seem like that much. Then you start importing dozens of modules, and it goes up to like 50 milliseconds, 100 milliseconds. We measured that in Mercurial's test harness, which the way it works is it executes the HG command and then compares the output. And it's a kind of a wonky test setup, which I could give an entire talk about. But it's it invokes Python processes over and over, thousands of them. And we measured that the overhead of starting the Python interpreter thousands of times during the test harness and loading all of the Mercurial Python modules consumes something like 25 or 30% of the runtime of the entire test harness. And so this is all overhead from Python startup itself. And this is a general problem in Python. We ran into this in the Firefox build system. When you invoke Python for thousands of times for doing little miscellaneous things as part of the build, like this translates to minutes or dozens of minutes of CPU time. It's kind of clown shoesy. And so PyOxidizer helps with this by substantially reducing the amount of system calls and I/O required at startup time. In the worst case, it's 0.1 millisecond faster per import. And that's in like the worst case on modern hardware. If you go somewhere like a Raspberry Pi where I/O is really slow, like this can translate to several hundred milliseconds or seconds pretty easily. Another thing here is that with PyOxidizer, you have single executable, and the size of that executable can be quite small. So if you have a typical Python installation, it's something like 3,000 files. With PyOxidizer, if you have just a simple hello world application that's stripped of everything, you can get down to, it's like 3 or 4 megabytes. It's extremely small, and considering you're getting a full interpreter in a few megabytes in 2019, that feels pretty amazing, especially since like this is probably what you'd be looking at for a normal Python install, like a binary on your system. So it's quite a substantial reduction. But what's more, I think, important, how am I on time? What time is it? Good. What is, I think, more important and it's more relevant to this group is what PyOxidizer can do for Rust and for Python. And PyOxidizer, my vision for it is that it empowers both of these languages to access new domains and features. If you're coming from Python, single file self-contained applications can give you access that you did not have before. So take, for example, the Ansible systems management tool. It's a Python program. But to run Ansible on a server, you have to have Python installed, which is, it creates this chicken and egg problem. And Python has this huge problem in reality where people aren't deploying like the latest versions of Python. So if you're a project like Ansible, you have to tell people, oh, you need to install Python on your server before you can use Ansible. Or if you're building Docker images, you have to install Python before you can use anything in Python. And then getting a modern, up-to-date version of Python installed can be quite laborious. So if you have a single file executable, you can just SCP that executable somewhere, copy it somewhere, and it just works. Pretty empowering. It enables application developers to target the latest version because the Python they're getting is the newest version. You can imagine use cases in places like AWS Lambda, any place that allows you to execute an ELF executable, you can execute Python. You just have a single file binary. From Rust, if you're a Rust developer, PyOxidizer allows you to easily embed Python to your application just by embedding a crate. In reality, it's not very well polished right now, but I can't publish the crate on crates.io because of, I think, restrictions with modified dependencies, I think. But in theory, you can vendor the PyOxidizer source code or reference it, and you can use PyOxidizer's build system to embed Python in a Rust application. And PyOxidizer abstracts all of the ugliness around, how do you build Python, how do you integrate it, link it into your Rust application. Where things really get interesting is the potential to unlock hybrid Python and Rust applications. And this is what personally excites me. PyOxidizer will allow, if you're a Python application developer, you can, once your application is oxidized, it's effectively a Rust application at that point. And so you can start chipping away at the pieces implemented in Python and port them to Rust. It means that as a Python developer, the world of Rust dependencies and crates are available to you. And there's a lot of fantastic crates for Rust, a lot of low-level systems things that, quite frankly, the Python community doesn't have as ready access to. Some examples are up there. I'm not condoning doing this. But like if you really wanted to, like a command line application could ship their own terminal emulator. For years, the terminal emulator on Windows has been really bad. Microsoft seems to be doing a good job of improving it, but I don't think it's quite there yet. But if you could ship your own GPU accelerated terminal emulator with your program, that's pretty neat. This matters for things like Python is really big in domains that aren't necessarily programmer heavy. A lot of data analysis people are using Python projects like Jupyter Notebooks, which are kind of these visual GUIs that allow you to do really cool data analysis. It's Python under the hood, or a lot of it's Python under the hood. But if you could make something like a Jupyter Notebook a self-contained executable containing its own browser rendering engine, and you didn't have to worry about installing all of these dependencies and shipping all these DLLs, like, I think a lot of that can be very attractive to application developers. Another example, shipping a robust HTTP2 server or client. I don't think Python has one in the standard library right now. I would love and I quite frankly don't trust random network protocol implementations. I trust things implemented in Rust. And so if you could say, oh, well, I want to use a Rust crate to provide my networking stack from your Python application. Pretty cool, I think. There's also a lot of other ideas around how PyOxidizer could be used to accelerate the capabilities of Python interpreters themselves. I find like the canonical Python interpreter is implemented in C, and it's kind of hard to hack on. But if you are embedding a Python interpreter from a Rust application, it's a lot easier to kind of hack around with new features and new capabilities of the Python interpreter. A couple ideas I've had here are to integrate a profiler implemented in Rust. It's easier, I think, to do that in Rust than in C. Debug servers. There's a lot of crazy stuff you can do. Swapping out the implementations of like Python's core classes and replacing them, because the way that PyOxidizer works is it combines object files to form a new Python distribution kind of on the fly. So if you wanted to, you could say, I don't like Python's dict or list implementation. I want to create my own. Mercurial would love to experiment with this, because every few releases there is inevitably a bug where we have a list contains in a loop somewhere, and we have an accidentally quadratic situation on our hands. And so we've hypothesized a few times, wouldn't it be really cool if we could test for lists where contains is called multiple times during a test, because it's almost always a bug to be calling list contains from Mercurial. We would rather use tuples or sets if we're doing membership lookup. So there's tons of ideas of how we could extend the Python interpreter. Say what? Which Python? Oh, boost.python? I've never used boost.python. Okay, cool, thanks. Yeah, so PyOxidizer, it's still, it's a relatively new project. I only announced it, I think, 6 weeks ago, and I've been enjoying summer and not hacking on it as much the last few weeks. But it's still actively a work in progress. There's a lot of things that don't work. This whole model of shipping a single file executable, like it completely flips a lot of assumptions in the Python universe on its head. Like a lot of Python modules assume that file is an identifier that prints out the current file name, and there's no files in PyOxidizer. And there's a lot of stuff in the wild where C extensions are compiled very weirdly, like NumPy. The Python's build system for C extensions is called distutils, and there's projects like NumPy that vendor their own copy of the build system and completely undermine efforts by PyOxidizer to change how things are built. It's pretty wonky. You have a question?
Yeah, so if you were to have file to point just to the current executable, what problems come with that?
Yeah, so the question is, what happens if you point file to the current executable? A lot of Python modules use file as a way of locating resources or files relative to the current file. So you'll say, oh, I have a JSON file next to my .py file. They'll look at py, strip the file name, strip the base name of the file, and then join the directory name with the JSON file name, and then attempt to open that path directly. There is an API in Python for accessing resources like that, but it hasn't been stable for long enough for people to use it. And so nobody uses it in reality, even though they should. I have a massive FAQ on the PyOxidizer docs about this. Like, I think every Python application using file is arguably wrong because, but like that's a religious war, and I know people like Google attempted to fight. Like Google has had single file Python executables for ages using different techniques, but they ran. My understanding is everyone who's done this runs into the same issue with file reliance on file.
I'm trying to use the microphone. I'm being polite. Everyone else is throwing their hands up, and they should wait for the microphone, people. I'm Paul Borrell from Earth Computing, and the question I have is, why is it easier to implement a profiler in Rust than in C? Can you say more about that?
I would say it comes down to personal preference. In the case of profiling, that's very low-level things, mucking around with internal state. I get to this afterwards. I have a few slides to finish the talk about my personal thoughts on Rust. And I just think that in 2019, I don't want to be writing any more C code. I've introduced too many security bugs and crashes. So, but where was I? So while PyOxidizer does have, the main goal is to make it easier to ship Python applications. Like, we're not quite there yet. We can build the single file executables, and people who already have distribution systems set up, or if you're in corporate environments, you probably have already solved this problem. So it's good enough for you to use today. But I really want to be able to, like on Windows, produce an MSI installer, on Mac, produce a DMG or a package, on Linux, we can actually produce a single file statically linked executable that you can just copy around and it just works. But I do want to make it possible to produce like RPMs and deb packages. And these are largely solved problems. The unsolved part is how to integrate them into PyOxidizer. Again, I want to make it really easy so Python application developers can focus on building good applications instead of toiling with build systems and distributing their applications, because it's really a time-consuming problem. And I thought I would use some time up here to talk about my feedback about Rust, coming from someone who's used mostly Python and C for the past 5 or 6, well, basically my whole career, which is more than 5 or 6 years. Talk about my experience coming from those backgrounds. I think maybe the Python background might be more insightful. I wanted to say that learning, the efforts gone into teaching the language improved substantially between 2017 and 2018. I tried to learn Rust over Thanksgiving and Christmas in 2017 and didn't have much success. Came back a year later, and I was able to build PyOxidizer with what I was able to learn. So that was impressive. I think the really biggest, this is a long list, I'm not going to go through it, but the thing that surprised me the most about Rust coming from Python is how expressive Rust can feel. I naively assumed that Rust, being a systems language, is going to be very low level. What I actually found out was that it feels like a higher level dynamic language like Python sometimes. And I was really shocked by that. So much so that, I don't know if I put it up here, but I think that for me, starting most projects now, I would choose Rust over Python even. And I'm surprised by that result, actually. I would say there are some edge cases, and people can ask me about these afterwards. I don't want to go through them. I'm sure the Rust community has beaten this horse to death multiple times. And yeah, I guess I did put it up there that I would choose Rust over Python. I would also say that a lot of people get hung up on performance. It's like, oh, is Rust or C or Java faster or whatever? Coming from Python, Rust is pretty much always going to be faster, because literally every line in Python, unless you're in PyPy, every line in Python is the equivalent, every variable is the equivalent of an RC or a .clone or a hash map lookup, because that's how Python works. And so if you are fighting the borrow checker and you get into trouble, you're tempted to clone your way out, like you can do that on practically every line in Rust, and you still come out ahead of Python. So I feel a little dirty doing that I should actually learn how some of this stuff works, but yeah. And that's it. Are there any questions?
For questions, just raise your hand and we'll route a mic to you.
Thanks. How does it compare to things like AppImage that also lets you bundle an application and its resources or dependencies in a single file for distribution across many systems?
Yeah, so it's very similar to AppImage in some regards. AppImage is obviously Linux specific, I believe, or maybe there's BSD support or something like it. Conceptually very similar. I wanted to focus on a solution for Python that worked across all platforms and worked in a similar technical manner across platforms. Because the current status quo in Python is that to do this on different platforms, like you'll have PyInstaller on Windows, and you'll have something else for Mac, and you'll have something else for Linux. And I wanted to unify all of these so package maintainers don't have to think about it. And AppImage seems cool, and I imagine that PyOxidizer at some point will spit out app images for the Python applications. Does that answer your question?
Oh, hello. Hi. Is there a fallback if you mentioned you have the include bytes macro? If somebody tries to import something, is there any kind of fallback to the file system where it would stat and try to find modules at a known location?
It's not enabled by default, but you can enable it and make everything work just like a normal Python distribution.
Thank you, and I'm sorry.
And so, well, in PyOxidizer right now, it's somewhat opinionated, and it really wants you to get towards a single file executable. But there's nothing saying, like, PyOxidizer can produce a single file Python binary that functions just like the Python that you would normally compile yourself. If you want to do that, you can. It's just that I haven't focused on building those features out as much, because the single file executable is like the holy grail of distribution, and I wanted to solve that technical problem first to prove that it was solvable before moving on to the lower hanging fruit. And I fully anticipate running into problems with like random C extensions that I will not be able to coerce into compiling the right way for them to be distributed. And I'll just have to give up and say, okay, those extensions, you don't have a single file executable, which, fine.
Hey, Gregory. This project is really super cool, and it makes me much more interested about mixing Python with Rust than I was previously, though I have done so on previous projects. From kind of a selfish perspective, I see that part of your plan is to automatically create platform-specific installers, which is kind of a holy grail, which you may even have mentioned that term. And I'm wondering, selfishly, if you solve this for single executable Python binaries, might you just go ahead and solve it for Rust in general?
This thought has crossed my mind, and the answer is yes, because what I am kind of doing here is from the perspective of Rust, these applications we produce are Rust executables. There is some other stuff that happens after the fact, like what PyOxidizer is doing is it invokes its own build system and then invokes cargo, telling cargo where to find its build artifacts, and then after it invokes cargo, it can copy files around and things. And so I initially started this, I wanted cargo to be the driver, but then I realized that the users of this application aren't necessarily Rust developers, and I didn't want to leak the existence of cargo to them. And so we actually wrap cargo. But all of this is, I'm very diligent about designing and implementing software as libraries. One of my programming mantras is everything is a library, and I purposefully try to make everything that I build as modular, maybe not architect astronauting modular, but I try to make everything a library first and then stick on the interfaces afterwards. And so when I build the distribution parts, they should be, if I follow my normal standards of programming, should be a well-isolated Rust crate or something that could easily be extracted for packaging. And other Rust applications or projects could come along and use this for their own distribution needs.
Super cool. I'm glad you're thinking about that. And I bet you when you get to the right point, if you just kind of like mentioned this on our Rust or something, people would just like come out of the woodwork to help you with the Rust side. Like you could just focus on Python yourself.
Yeah. But let's not make it our Rust because that place is a little toxic.
Well.
But yeah, I can mention it.
Cool, man. Yeah. Thank you.
2 questions over here.
Yep.
Have you considered PyPy? The first question, have you considered PyPy? The second question is, how do you handle the Python module dependencies? Like you import, if something, you import some module, else not import this module.
So, okay, first question is on PyPy. The mechanism by which PyOxidizer consumes the Python distribution, I designed it to be generic and abstracted. So the Python distribution that PyOxidizer consumes is a tarball with an install of Python, a whole bunch of object files and static library files, and then a giant JSON file describing what all the object files are. And so in theory, and I haven't done this, but in theory, someone could come along and produce a PyPy distribution that has that conforms to this tarball format, file layout, and PyOxidizer would consume it just fine, because to PyOxidizer is just telling the build system how to link a whole bunch of object files together. So it's definitely doable, and I really want to experiment with that sometime. The second question is about conditional modules. By default, PyOxidizer does not sniff which modules you use or attempt to parse the source code. A lot of the Python distribution tools in existence will look at your Python source code and try to extract, oh, you're using this module, and I need to include it, and then they'll throw out all the modules that are unused. Very brittle problem space. There's always false positives, false negatives. PyOxidizer does support stripping out modules, but it doesn't do any type of source analysis. One of the cool things I did in the Rust code is you can build an instrumented binary with PyOxidizer that if an environment variable is set, when the executable exits, it will write out a file listing all of the Python modules that were imported. And so what you could do is you could build an instrumented binary, dump out dozens of files listing all of the modules that were imported from like your test suite, and then use the set of all those modules as a filter list of what to include in a final binary. And I think that's a more robust solution than parsing source code.
So you mentioned using PyOxidizer to take advantage of like replacing the list implementation in Python or dict. What are the iteration times with PyOxidizer when you do something like that?
There are build system overhead times that are problematic for PyOxidizer because I mean I'm not embedding the Python distribution in the PyOxidizer binary, but in that case, if you were to replace an object file, you would have to consume a new Python distribution. It decompresses in a second or two, I think, that the Python distribution does, and it reads the metadata. That's usually pretty quick. For me, the slow part is compiling and linking Rust.
So my only experience with this similar kind of application before are PECs.
Yep.
So if I want to think of, so you mentioned that we can run any of the executable in a certain way, which can provide us an interpreter, right? Or is it to be? How do you actually invoke them? When you invoke the interpreter, do you get a prompt where you have all the embedded modules available as part of the environment?
Yeah, so when you build, there's a TOML file that configures the built application, and that TOML file defines the default execution behavior of the Python interpreter. And it can provide a REPL, a Python REPL. It can execute a line of Python. It can eval a Python string as code. It can execute a module as the main module. There's different modes there. Those are the pre-canned modes. If you want to go lower level, you can instantiate your own configuration from Rust and tell it explicitly what to do. So if you wanted to have some Rust code running before and then dynamically build up the Python code to execute in the interpreter, you could do that.
I mean, suppose you have a executable for, say, Jupyter, and you invoke the executable in a way that gives you the interpreter prompt. Will all the modules of Jupyter and NumPy and Pandas be available in that interpreter session?
Yes.
Can I import them and have access to them? So
yeah, that's the idea.
Okay. The second question, very quickly, is how do you do debug in this in PDB? How do you link PDB in this in a way that, because PDB works a lot into file locations and stuff like that? How do they work in such a installable?
I've definitely debugged. I've used PDB in PyOxidizer binaries, and I think it just works. I guess I don't really set breakpoints based on files. I set them based on modules, and that PDB is not confused by that. And PDB is part of the Python standard library, so unless you've stripped it out of the application, it's there and it's available.
Hello, I work at Twitter on Pants. Think this work is super, super cool, and PyOxidizer, one of the issues we have open is how to ship Pants as a static executable, even just so we can avoid having to package Pants for every single Python distribution. So import time is something that you can literally even see with Pants. So that's really, really cool to me. Pants is also written in Rust and Python, and that's very, very cool. And we're looking at PyOxidizer to perform that. When I say we're looking at it, I am seeing it, and it's very cool. The question I wanted to ask was, yeah, this project is fantastic. The question I wanted to ask was, are there other systems that kind of do the importing from memory a bit that you're doing with PyOxidizer that you drew inspiration from? Because I mean, I can definitely see obviously why it's super effective, and partially it's because I'm trying to make Scala compiles really, really fast right now, and part of it is something vaguely related to having class files in memory, for example. So I thought that was a really, really interesting talk, and I didn't know if you have any inspiration for that.
I knew that there were other tools that had done it before. I know Google has had single file executables for years, but they used non-conventional means to achieve them. I think I'm aware of the technical details, and I think they're open source, but I'm not confident of that, so I'm not going to elaborate. But I knew that others had achieved the problem, just not in a cross-platform and open source way. And so that gave me the confidence to try to explore this area and do something to figure out how to do it the right way without grotesque hacks. One more, I guess.
So you expressed previously that build systems can be very frustrating. What are some of the experiences you had that were actually fun or fascinating in this area?
I feel like I'm trying to find a needle in a haystack here. I would say teaching the Firefox build system to use Rust. I wasn't as involved with that as some other people on the team, but that was an extremely rewarding project to be part of, to see Rust grow at Mozilla as a research project to a tangible language in the span of a few years, and then to actually go through all the controversy and technical due diligence of how do we actually ship Rust in Firefox, and to see it actually land one day, that was special. I felt like I was part of history to ship Rust in a product used by millions of people.
Awesome. So that's all the time we have for questions. Give another big round of applause for Greg. Thank you so much. We'll have a brief 5-minute bathroom break, so if you need to use the bathroom, go do that. Also, if you need more hydration so you can use the bathroom later, please help us with our beer problem. Thank you. We'll start the next talk in 5 minutes.
Thank you.
All right, so this next talk is by Jeremy Fitzhardinge, who is one of my coworkers at Facebook. Jeremy is the tech lead of the Mononoke project, which is a Mercurial-compatible source control server written in Rust. He also works on Facebook's Rust Foundation team, which supports Rust throughout the entire company. Now, the Rust Foundation team makes it sound like Rust is an first-class language at Facebook, and that's maybe going to be true in the future, but it wasn't always the case. So Jeremy will be talking about the process of bringing Rust home to meet the parents. Take it away, Jeremy.
Thanks. Hello, I'm Jeremy. So we all love Rust. We, have been using it in a various capacities over the time, but now it's sort of time to bring it into the rest of our lives and set it up for success. So that's essentially what I'm going to talk about, how I am trying to do that here at Facebook. So about me, I've had about 30 years industry experience, a lot of it as doing low-level system software, a lot of it pure C in kind of kernel level and below the kernel, and a fair amount of C++, and I've seen all the things that can go wrong. And when I first encountered Rust a few years ago, I was completely taken with it just because it was the first language I seen that could replace C in every role where C is predominant, while genuinely adding a whole new dimension to expressiveness and safety. I've been at Facebook for about 3 years now, and it's the first time I've deliberately joined a large company. And so in a lot of ways, I've been learning how large organizations work in parallel with doing this Rust introduction. All my previous career has been in very small companies and startups, and I certainly know how you'd introduce new technology into those environments. So this was an interesting new challenge for me. Yeah. So when you introduce a new language to an organization like Facebook, you have to make a case for it. And the case has to be not, it's a better language. It has to be a lot better at something. And it has to be at least as good on every other front. And that's because introducing a new language is not just a technical issue. It's as the previous talk said, like a language is an interface between what you want to do and the means to do it. So a new programming language is an intrinsically risky proposal to introduce it into your workday, because you end up with a bunch of code written in this language, and if it doesn't pan out, then you've got a huge amount of extra tech debt. And Facebook is full of engineers who are very pragmatic, and they're primarily interested in getting their jobs done. And so when you say you can do your job, but you have to learn this new language to do it, you really have to have a good reason to even consider that. And so Rust has to not just be better, it has to be worth everyone's time. It has to be the best tool. So when I say much better, let's say it has to be 10 times better at something. So what is Rust's proposition? Like, what is Rust 10 times better at than any of the incumbent languages, say, for example, C++? The win here is that Rust safety guarantees detect large classes of serious bugs at compile time. And the earlier you can detect a bug, the much cheaper it is to fix it. So fixing something in a compile loop when you're sitting there in your editor is many orders of magnitude less than finding it 3 months later when you're running around because you're looking at the headlines saying Facebook is down. So what are we talking about here? What's the environment we're introducing Rust into? I'm talking primarily about back-end services. We have lots of different kinds of code within Facebook, but I'm mostly sort of in the back-end space, and so I'll talk about that. We have like 3 dominant languages that are most of the lines of code and probably most people's programming time: C++, Java, and Python. The C++ and the Java tend to be services, and Python tends to be glue holding everything else together. But our code base is extremely polyglot. We have lots and lots of languages in use for specific reasons or just because legacy, we tried them out and don't use them anymore. But you know, we have small languages that are used nevertheless for huge services that are vitally dependent, like Facebook vitally depends on every day. So the reason for that is that teams have a lot of freedom about choosing what technologies, what languages, and so on that they get to use. But that doesn't mean that they can just go off and say, oh, I'm going to do this project in brainfuck because why the fuck not? It's going to be, they have to have a good reason. And other people are going to ask them, like, why did you choose brainfuck? You know, it's got a really good debugging environment. So it's not just a matter of saying, oh, Rust looks cool, let's try that out. It's like, well, how's that going to fit in? And this code base we're talking about is huge. And when I say huge, it's not like each of these individual languages have their own sets of lines of code, but they're all in one great big source repository. We have a single, like, well, as Arun likes to say, we like monorepos so much, we have lots of them. But we have 3 big ones, and all the code I'm talking about here is in one. So it's got millions of files, and it's got hundreds of millions of lines of code, and there are like many thousands of commits a day. And to make that work, to make that practical, like if you imagine setting up a GitHub account and saying, oh, I'm going to put 5 million files into here and blah, 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 that's going to feel very unpleasant. So to make that work, we also have to spend a lot of effort on specialized tooling. So pretty much every aspect of our tooling is tuned to this environment. Everything from source control to build, CI, blah, 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 everything. And it's all with one sort of overwhelming goal, which is that the amount of time you spend waiting on tools, the amount of time that gets into your inner loop, should be proportional to the size of your project. So if you're working on a 100-line server that you're just editing and compiling, it should feel like you're working on a 100-file repo. If you're changing one of the core libraries header files that affects every single C++ project in the system, you're going to be waiting a while for that. But you know, most people aren't doing that. So what does that look like from a Rust perspective? Well, let's look at the Rust view of the world. Is this going to work? Oh, surprise. All right, so I think it's fair to say that Rust values the safety aspects of the language very highly. It's sort of the underpinning of everything else. That if Rust didn't have the safety aspect, it would be a cute, interesting language, but there wouldn't necessarily be a lot of reason to pay attention to it. But that said, it's a new language, so there's a lot of scope for experimentation. There's no baggage, there's no prior art. We can like choose to do things the way that we want to. And so, despite that, one of the core values of Rust is this idea of stability, that the language and the standard library change in a very measured way, and they always have backwards compatibility, or when they break backwards compatibility, it's done in a deliberate way. And to offset that, there's a very vibrant third-party ecosystem based around Crates.io, which allows for lots of experimentation, lots of dynamic trying out new ideas, without necessarily committing anyone to any one of those. And then to make that work, there is Cargo, this tool, which manages build and dependency and offers a very low friction approach to the language. Like a lot of people's first experience with Rust, when you see them sort of say, oh, I love Rust, I tried it out. And what they're saying is, I tried out cargo and it just worked. It's so easy to add dependencies. I add a thing, you know, and it's like a huge selling point for the language. So as a result, in a lot of ways, cargo is the center of the Rust universe. There's the compiler, and that has a very important role, but sort of off to one side. It's cargo that's in the middle, orchestrating everything around it. So as a result, cargo has this very heavy bias towards Rust. It treats essentially the entire world as Rust or other, and other gets a very short shrift. And so basically, non-Rust is a non-goal for cargo. So that means that cargo alone is not enough for us. We have this very complicated environment. We have lots of things going on. And so how can we bring Rust into our environment while retaining the essential benefits of Rust and also the essential benefits of our development environment? So why are we even talking about Rust? Why is this a thing that is a subject of conversation at Facebook? When I joined 3 years ago, I joined the source control team, and there was basically this project sitting on the shelf saying, we need a new source control server. We can see the shapes of the lines on the graphs, and we know what Mercurial's upper limits are, and we can see that in about 2.5, 3 years, those lines are going to cross, and we don't have a good plan for that. So let's do a new source control server that can deal with the scale that we anticipate over the next few years. And so that was the immediate motivation. We need a new thing. But we also know that Mercurial's model is good for what it's good for, but it wasn't good for a lot of things that we wanted to do. So we wanted to have a new server that could enable a whole bunch of new functionality. It's not, and so it's not a Mercurial rewrite, and it's not even particularly Mercurial compatible. It just has to fit into the same slot as Mercurial, but also do a lot more. And being a source control server, correctness is essential. Like, randomly corrupted source files is a complete non-starter. And if, you know, even had the hint of that possibly happening, it would be extremely bad. But it had to be in a compiled language because we're replacing something in Python, or replacing something with something else in Python when scalability and performance is a concern doesn't really make a lot of sense. So, long story short, 3 years later, we've deployed Mononoke now as the backend, the source of truth for the big repo that I'm talking about, the systems backend services repo. And it's been working out pretty well. And our experience on the server side was good enough that the client side of the Mercurial team has now been, or the source control team, has been doing all of the new client-side development in Rust as well. And so our experience of bringing Mononoke into production showed that the claims checked out. That basically we spent no time debugging memory corruption issues, race conditions, memory leaks, those sorts of things. It's so hooray. And nevertheless, we still see core dumps in production. We see stack overflows because we have some overly recursive code. FFI to C++ is kind of interesting. If an exception escapes through there, we end up with a process termination that's a bit surprising. And actually buggy C++ code, but never buggy enough to actually cause really difficult corruption issues. One of the interesting things about this was I also chose to use Tokyo Async, and pretty much I started the project the day that Crates.io got its first Tokyo update. So in a lot of ways, that was a big bet, and it turned out in the end pretty well. So overall, the experience was good enough that I could make the case saying it's worth and justifying this for, justifying further investment, and let's see how far we can take it. So I talked about the 10x advantage. What does it really mean for Facebook? What is the cost of a bug? So, as I said, when you see a headline, Facebook down, Instagram down, something like that, what that means internally is a lot of running around, a lot of shouting, a lot of looking through log files and digging things up. But fundamentally, it means that's a huge amount of lost revenue. Like, that's a lot of lost revenue. It doesn't take much downtime for that to be many people's salaries worth of lost revenue. So, and at least some of those failures, by no means all, but some of them root cause to, there was a use after free in this service, and it was like 5 hops away from anything that you would actually see on the front end of the website, but that was what the root cause was. And so because of that combination of cost and fallibility of the software environment, we spend a lot of effort on ways to try and mitigate that. Everything from extensive code review, lots of investment in static analysis technology, lots of test infrastructure. But the end result is they're all a bit too late. If you're sitting there working away in your code, and you're typing away and you hit compile, and you're typing away and you hit compile, when the compiler stops complaining at you, in a sense, no matter how experienced you are and how cynical you are about correctness, you say, well, job's done, something will sort it out. You ship it off, you go send it out for review, and then you go on to the next problem. And then an hour, 2 hours, 3 hours, a week later, someone comes back and says, oh, I think there's something weird about the locking here, or you sure this is correct? Or the static analyzer says, here's an enormous chain of things that you should trace back to work out why this was broken. And the context has gone out of your head. Whereas with Rust, a very large class of these problems are just compilation errors. So while you're sitting there in your inner loop, editing, compiling, you're sorting out very fundamental problems before you even commit the code. And then other languages have those benefits, like people say that about Haskell, that once it compiles, it works. But the nice thing about Rust is that it looks a lot like C++ operationally, that the final executable is a standalone ELF executable. It's got dwarf debug information. It has OS threads. It uses system malloc. You can use your heap profiler. You can use your other instrumentation. You can use fleet profiling. It just looks like a C++ binary as far as everyone who's concerned about it as a deployable artifact. So it's very appealing in that way. But one of the really difficult things to work out is what's the cost of bugs that didn't happen? If your whole thesis is that Rust solves your bugs, not having bugs is a kind of very negative signal. So that's a thing that we really have to work about. Like, we don't yet have enough experience in putting Rust into production to be able to work out, like have direct side-by-side comparisons or anything like that. So, you know, that's a thing we're working on. But there's a whole bunch of secondary things, like I mentioned code reviews before. With Rust, because you can trust on the compiler to give you errors about a whole class of relatively low-level bugs, it means that the code reviews only have to focus on the high-level aspects of the diff, like, is it, you know, design, architectural details, you know, the why is the code this way, not how does it work in precise detail. And so that's roughly, I would, you know, complete hand wave, 50% of a C++ reviewer's effort is now eliminated. And then there's also the lower risk of code maintenance. When you're writing the code in the first place, you have a complete mental model of exactly how it should all fit together. You sit there, you know what all the constraints and the invariants are, you write them all down into a piece of code and it works first time. Hooray! You wander off for 3 months and someone needs to go and do a change, probably you, and then you go, let's put a new if statement here. Here's a case that we need to look at. Plonk it in, it compiles, ship it off, and then 12 hours later, like just as you're getting to sleep, then you get woken up saying, that thing you landed to solve that emergency bug caused even more problems. Whereas in Rust, if you can encode all of the invariants of your, of your code in the type system and in the lifetimes, then it means that you're not going to be able to just plonk in something that's clearly broken. You have to get it past the compiler first. And so it means that your internal estimation of the risk of making this change is that it's less risky doing it to this code because I won't be able to land anything truly broken. I mean, of course, that's not really true because you can break it at many other levels that aren't covered by either Rust inherently or by your design, but the bar is a lot higher. So, that said, who is actually adopting Rust? Well, the surprising thing is, given the amount of time we've talked about C++ bugs, by far the most enthusiastic early adopters were the Python programmers. They basically, there was a pool of Python programmers who set up a game for themselves of, let's convert my favorite Python script to Rust. And what they ended up with was a whole bunch of Rust that looked like Python in Rust syntax. But the effect of that was there was a whole bunch of people who are now suddenly a lot more confident in their ability to get something going in Rust, that it wasn't completely weird and mysterious. It was just a programming language that they could get stuff done in. And as Greg talked about, like one of the enormous costs of Python is just startup time. We have little services on every machine in the fleet that pop up every minute, read a few stats out of /proc, shove them into a management interface thing, and then die off. And their job is very short-lived. So the proportion of the time spent starting up Python is enormous in those cases. And converting those things to Rust easily paid for its own effort, like probably paid the engineer who did its salary for that year, just in terms of savings. And then since then, there have been people who've been converting their favorite, more complicated Python scripts where they actually want types, or they want more closer, tighter control over resources. And runtime performance, like of inner loop algorithms, is relatively less important compared to those. There's been a lot of people converting from Node, JavaScript stuff, like developer tooling, into Rust. And so these are communities that typically you would say are not good candidates for understanding Rust, like going from a reference counted or garbage collected environment to being made very well aware of exactly what your lifetimes are and how you're allocating memory and all that sort of stuff. Doesn't seem like a good fit. But I think it really comes down to the fact that because the compiler does have very good error messages and they're very actionable, it means that someone who's in that inner compile loop, not really knowing the language, but also not being allowed to do things that are horribly broken, they eventually end up with something. And what they end up with is something that does what the source code says. Whereas if you're a C++ programmer, you can look at the source code, and then you can look at your segmentation fault, and you can look at all the manuals, and you cannot draw any connection between those. And so you end up with something that doesn't work, but it does what the source code says. So then you fix the source code, and then you end up with something that works. And that's a positive experience. And in particular, like the startup cost is very expensive for command line interfaces. We have tons of them. And it's kind of important for a command line interface to like come up and do something like show a usage message in 100 milliseconds. But a lot of our CLIs are written in either C++ or Python, and the Python ones suffer the startup cost even more. Like there's a very widely used tool that takes 5 seconds to show its usage message. It's infuriating. And so it turns out that Rusters are really good at doing these quick startup things. Like the combination of clap and struct-opt has like sold many people on Rust. And I don't know if you're familiar with struct-opt or clap, but clap is sort of like a general command line library. And struct-opt is a wrapper around it which uses procedural macros, so you can just define a structure that declaratively defines what your command line interface is. And it's very expressive, and it's really nice. It gives a very good first impression. So we have all of these new Rust stations. How do we support them? Well, most of the teams who've decided to use Rust have not had any experienced Rust programmers on them. They've basically been buying the legend, buying the myth. And as a result, like part of that is being very careful to make sure that expectations are managed and that they're not going to get magical fairy unicorn things unless you choose the right libraries. So as a sort of universal concern of that is how long is it going to take for my team to ramp up? How much time am I going to have to write off from this next quarter saying that we're not going to get anything done because we're all learning a new language? And the answer is some, but not nearly as much as people expect. Like, these are very rough numbers, and I'm very hand-wavy about these, but I think it's reasonable to say that people spend about 2 or 3 weeks just fighting the compiler and the language and being shouted at and getting the basic principles out of the way. But then within about 3 to 5 weeks, people feel reasonably confident about being able to get something working. Like they have an idea in their head and they can kind of work out how to express it in Rust. It's not necessarily elegant or pretty or anything, but it gets the job done. But then after about 8 weeks, people actually start getting genuinely competent. They feel like they're beginning to use the language idiomatically and get stuff done. It does depend quite a lot on what language background that the individual has come from. Functional people from a functional background tend to have the best experience, or like Rust is the most liberating for them from a more constraining environment. C++ programmers, once they work out how Rust's conception of lifetimes clicks with the model that they have to have had in their head to be a successful C++ programmer, then that all just works for them. The people who have the worst time are coming from like Go or Java, where a typical program is an enormous tangled mass of goo in a mutable heap, and it's pretty much essentially impossible to represent that kind of structure in Rust, or certainly not idiomatically. The biggest danger period is probably 2 or 3 months after the consistently idiomatic, when someone gets in their head, I understand traits now. and then you end up with things with 15 type parameters and, you know, billions of constraints and, ask me how I know. So one of the interesting things is that the existing learning materials are really good in the external world. So we haven't actually had to produce very much internal material. Certainly not about basic language stuff. There's a fair amount about specifics of getting Rust to talk to weird Facebook infrastructure X, but in general, the learning materials are really good. But part of that is building a community. So one of the important criteria for having a language within Facebook is that there is an internal community, so that a team is not working in isolation, that if they have questions, they're not entirely on their own working out how to resolve those questions. So we need to have and maintain an internal community that's very much an extension of the external Rust community. And one of the things that non-technical aspects of Rust that I find delightful is that it's making sort of genuine successful experiments in how to build a community around a programming language. There are so many really negative examples that anything would be an improvement, but I think Rust is genuinely taking this approach where a level of emotional safety about interacting with a community is a foundational principle of having a healthy community. And so so that's one of the things we want to make sure extends to the internal community as well. Secondly, when you have a new team which has got a whole bunch of people who've never used Rust before and they all need to review each other's code, but they don't know Rust. So how do you bootstrap a review culture around a new language for these teams? And one of the basic mechanisms is we have this thing called Rust reviewers. It's sort of like a tag you can just put on your change, on your PR, and anyone who's subscribed to that can drop in. And I've been encouraging people who know Rust to do that so that they can help bootstrap other teams' Rust reviews, but also encouraging learners to watch other reviews going on. But because I think looking at other reviews going past is itself a very strong educational mechanism. We have a Rust at Facebook group, which is sort of general chit-chat, but we also have a Learning Rust group in which there's a very wide range of questions that people ask. There's, how do I achieve the same effect that I would get in Python or C++, to here is this complicated type thing, and I can see that there's, variance relationship here between these two types and this lifetime and, question. And then a PhD will pop up from somewhere and saying, well. And one of the other ways of making Rust fit into the broader Facebook community is to remove gratuitous weirdness. So we have this very open code culture where there's no sort of hard, like there's the original authors of a piece of code and there's the team that's currently maintaining it, but there's not a rigid line of like ownership where no one is allowed to look at my code. And when people are fixing things that are going wrong in production, they need to have wide leeway to be able to look at any code, and they need to be able to understand that code. So even if you don't know Rust, it ought to be possible to look at a piece of Rust code and at least know what subsystem it's part of. Like, what's it approximately doing? What's it interfacing with? So that you can say, well, this might be part of the problem, or this definitely isn't part of the problem. And so adopting existing conventions where they exist, where they don't strongly conflict with Rust's conventions, is very important. So like, if you're doing a binding to a C++ library, use the same names for the Rust types as the C++ types. And when we generate code from Thrift, our RPC mechanism, where you have a language-independent IDL, we use exactly the same names that the IDL specifies, even if it isn't exactly Rust's formatting style for, say, an identifier, just so that when you grep across the code base, you can see, oh, here's a hit in the Thrift file, and here's a hit in the Rust code. So we have a whole bunch of really enthusiastic early adopters. We don't really need to sell Rust on them, sell them on Rust. What we need to do is reach out to the people who want to get their job done. And Rust is one of the tools among many, and it's an interesting tool, but by far not obviously the best tool. Why should I use Rust? I've got all the C++ code, I've got all these C++ programmers, we have to fight bugs every now and again, but we kind of know how to fight these bugs. Why? And so this is a very incomplete partial list of some of the arguments that we kind of like float. One, from earlier, undetected bugs are really expensive. Like when they turn up and bite you at the wrong time, that's really expensive. Rust is intrinsically secure. It's like obviously possible to write insecure Rust, but you kind of have to jump through hoops. You have to make an effort. If you're writing some code that's touching random untrusted stuff from untrusted sources, I think it's probably it's certainly a very bad idea to do that in C or C++. Like, I think Rust should be the default for those cases. Rust is cool right now. So one of the side effects of it being like Facebook's philosophy, where teams can choose their own technologies and so on, it's also that engineers can choose what they choose to work on. No one can tell you what to do. If you feel that you have a better use for your time than what your manager is saying, then go and do that other thing. 6 months later, you need to demonstrate that it was a good use for your time, but it's kind of up to you. And so what that means is that there's a cool project over there that's using Rust, and it looks really interesting, and, oh, you want me to write 50,000 lines of C++? I'm going to go and talk to that team. And so teams are always in competition with each other to try and get the most enthusiastic people to work on their projects. And Rust is a little bit of extra on that. And then, as I said before, a Rust binary looks a lot like a C++ binary in production. So you can still use, like, the risk is in the language, the weirdness of the language, but that's where it ends. Beyond the language choice itself, it looks very conventional. And these general observations are not going to be true forever. But right now, as far as I know, no one told me otherwise, everyone who's ever evaluated Rust in the company that I've heard of has ended up deciding to use it. And none of them have decided that they didn't want to do that again. And so, for what it's worth, that seems like a good idea. And that kind of, for example, Libra went public recently, the Facebook blockchain thing. They went through a whole great big discussion about what language to do that in. And they certainly had Rust enthusiasts on the team, but they had people who are other language enthusiasts on the team. And they ultimately decided on Rust because management decided that it was actually the best trade-off between all the things that they needed to trade off. So, you know, as an example. So, where are we now? We have a solid start. We have several projects that are very high profile, very strategically important, that are implemented in Rust. And for that reason alone, Rust is not going to fade away easily. But, so that's a good start. We have many of the, like when I say standard APIs, I mean Facebook-specific internal things, but stuff that everyone expects to be able to access. Like, I want to access a database. I want to log some statistics. I want to, you know, do a whole bunch of things. We have those APIs now set up. so that it's relatively easy to write Rust code and just call those APIs. In general, and I'm talking specifically here about backend service development, the experience feels comfortable to Facebook developers. Like, aside from the specific choice of language that you're writing in your build descriptions and so on, the build process, the editing process basically feels very similar to C++ or other compiled languages. And it also feels quite comfortable to Rust developers. You can put a pound test in front of a function, and that becomes a unit test. And that's not using Rust's unit test framework, or it is a little bit, but it's also plugging into Facebook's unit test framework, which is much more extensive and keeps track of the state of every test everywhere in the entire system, and keeps track of the pass-fail rates and whether the tests are flaky and whether or not, what tests are associated with what build targets and what needs to get rerun one. So you get all of that just by putting pound test in front of a function. And there's a huge amount of ambient enthusiasm. Like, every time I mention Rust in public forums within Facebook, there's lots of people going, yay, we can use Rust. Go and use Rust then. But, but it's good that people are enthusiastic. But, we're not anywhere super substantial yet. Like, I mentioned dealing with untrusted inputs. I think Rust ought to be the default language for anything security related, anything dealing with untrusted inputs. We're not quite there yet. I think we can make that case, but haven't yet. The non-enthusiasts, the people who want to get stuff done, the Rust is not the obvious best answer to any of their questions yet. Or at least the threshold is still quite high. There would certainly be people who decide that Rust is the right language for whatever they're trying to do, but not everyone. There's some really big holes. Like, our use of RustDoc is abysmal. We're basically not using RustDoc at all internally. And that's partly because the RustDoc tooling is the hardest tooling to integrate with other things. It's the most weird. And in general, we just need a lot of polish. Like, we have an RLS implementation. It's working with Buck, our internal build system, but RLS really, 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 really wants to work with Cargo, and we don't have Cargo. So, there's a lot of polish yet. So basically, as we say in Facebook, this journey is 1% finished, and we could hire you all eventually, I guess, to work on this stuff. How am I doing for time? I have extra stuff I cut out, but questions?
So my name is Paul Borrell again from Earth Computing. I want to ask you, is there anything negative in your experience with Rust? What have you experienced that you wish was better?
Well, I'm not pausing because there's nothing. I'm just like, there's a balance. There's a lot of teething issues. There's things that are intrinsically wrong with Rust. There's things about the Rust ecosystem that I would like to change. There's specific details of the Rust integration with Facebook infrastructure, and then there's having used Rust in practice, where does it fall down? That's almost a whole other talk. However, I would say that the FFI, actually, what have we got? Can I do this? Here we go. So FFI question is quite rough. Like, we have a lot of existing code, and being able to interface with that efficiently sets a sort of barrier for entry that makes it quite difficult. And debugging problems around that is quite tricky. We don't have tools like sanitizers that work across languages, and none of our static analysis tooling does that, and that would be nice to do. Another problem is that because the ecosystem is so cargo-centric, it's quite difficult to get traction on, I want to do this in a way that doesn't involve cargo, or I'd like to involve cargo, but cargo has to make these changes to make that plausible. And that doesn't get a lot of traction because most people, cargo is a really good tool, and it does work very well at the scale that they're working at. And it's quite difficult to get across exactly what we're trying to do in this kind of environment. And I hope this talk has helped, but it's still a lot of outreach into the Rust community to get stuff going. Does that cover? Okay. And we'll go with that one too.
Quick question. Who's it first? I don't know.
Hello.
You mentioned that you were quick to jump on top of Tokyo Async. Could you explain why? And if you have a quick explanation, I might have a quick follow-up question.
So really because the previous project I'd worked on, which was a big non-async C code base at a previous company, and by the time we realized that we needed it to be async, it was basically impossible to retrofit. And so I made the early strategic decision that going async early was better than going async late.
So you didn't have any experience with futures pre-async then?
I mean, I'd written my own futures library at one point, but Tokyo and the futures mechanism around it is quite different from that. So that was certainly a steep learning curve for me and the rest of the team, particularly because of the lack of any syntactic support until recently.
All right, thank you.
Sorry. Yep. Quick note. There is one other 10x that you actually kind of browsed over on some of your slides.
Yep.
If you need systems level performance, Rust has a 10x over C++. And that is onboarding developers who have never worked with either. You mentioned the 8 weeks. That's pretty consistent with my experience onboarding Python and Node and so forth developers. And my experience to be trusted with a secure and, deployed in high stress environment C++ code base, a developer needs approximately 2 years, so a little over 80 weeks.
That is a nice point. I'll steal that. Thank you. Oh, by the way, in case you didn't realize, you're my test run audience. I'm presenting this at RustConf next week. So
nice. And one other question with regard to the shortcomings on Rust, have you or anyone else attempted to use it for something like a plugin?
So you mean having C++ code calling into Rust?
No, I mean in the sense of having a component that is a pretty much stable application that loads binary shared libraries written in the same language and expects them to be able to link against a library with stubs in order to know what they can depend on getting from the runtime and providing a stable, predefined interface to that thing.
So I could easily imagine circumstances in which that would be very painful. The lack of a stable ABI would make that very annoying.
C++ got around the lack of a stable ABI for years and it still worked. Rust's problem goes deeper than the lack of a stable ABI.
Well, I mean, there's sort of stable ABI, an ABI that changes every 6 weeks. But generally in our infrastructure, that kind of dynamism is very frowned upon. We deal a lot in statically linked things. So that has not been an issue, but I could easily imagine environments in which that would be painful.
So,
yep.
So you had mentioned earlier Libra and its usage of Rust. Recently, there was a member of Congress who had asked about Rust being used there. And so what are 3 points that anyone in this audience could use to essentially...
I can answer that now. They wanted async await.
But specifically to a non-engineer, what are 3 points that anyone in this audience can make towards the usage of Rust and why teams should be using it?
Well, I think the specific question, the Congress, Senate, whatever, question was about using the nightly version, and that was because they wanted to use async await, and they knew that async await would be stable by the time Libra was going to get wide use, and they certainly wanted to make sure that Libra shipping was stable by the time it's mass production or whatever the right term is. But in general, I think that 10x advantage of safety and the cost of bugs and the expense of finding bugs late in production when they actually affect the real world is a pretty easy case to make for anyone. And here, where everything is thoroughly measured and often has dollar values attached to it, it's pretty easy to say this. And as I said, the tricky part is saying, look, our production's been in service for a year and hasn't had any bugs. Like, so what does that compare to? But I think in general that's a tricky problem. Question. I'll alternate.
So when I when I started with Rust, I was the only Rust programmer in the building. There are only 3 of us on the team, but I would get a borrow checker error, compiler error, and I would stare at it and have no clue what it was. Now, being really stubborn, I would finally fight my way through, but I would expect that people would give up on that and give up on Rust because of that. At this point, I can bend the borrow checker to my will, but that certainly wasn't true early on.
So I think that's the importance of having a community around you, and like having someone sitting right next to you saying, like you know, the experience of you can stare at a borrow checker bug or any particular bug for hours and not make any headway, and then you can show it to the person next to you, and they go, well, why didn't you just clone it here? And like, oh, okay.
So as you're bootstrapping the Rust, you make sure that nobody's alone working on it?
So we have, like, for here, we have a lot of internal communities, and so making sure that Rust existed as one of those from an early stage. And, you know, things like code review, having people you can call in to help out with code review. And that person may be an expert in Rust, but not necessarily understand your problem domain, but that's enough to get you going.
By the way, the one thing that saved me was users.rustlang.
Right.
They're just wonderful.
Yeah. And that's kind of the experience I wanted to make sure was continuous to within Facebook as well as external.
So you do.
Yeah.
A question. You mentioned that the project, that Libra project, Rust is one of the components on which you are building it, correct?
Mm-hmm.
Any specific reason? I mean, we could have used C++ or Erlang, which was an OTP language. I mean, long back, a lot of telcos used it in the old days because it's more on the payment. I mean, eventually it will be a payment that you will be using, correct? It will be a transaction, money-related stuff that you will be doing. So, I mean, any specific reason that we chose Rust?
So I'm not on that team, and I can't really go into a lot of the details about what they considered. But I know that security, like not merely security, but being able to have strong provable properties about the entire system is very important. And so by eliminating undefined behavior or making undefined behavior have a very constrained bound, it makes it much easier to talk about the properties of the system as a whole, or at least analyze them. And that team has a lot of static analysis and sort of formal theory proving people. And so all the languages they were considering more or less were in that domain. And so Rust sort of ended up being the pragmatic middle ground between a whole bunch of competing concerns. But they're all very concerned about being able to say, like, have strong things to say about the properties of the system that they're building. And, you know, you can see that one of the products of that was that they wrote a new programming language for writing smart contracts in called Move. And the semantics of Move are very obviously related to Rust. And I would like to say that they derived those from Rust, but they certainly drew from the same sources.
Hello, can I just speak? Okay. So there's a great deal of obviousness about how Rust is good at memory races in single machines. What can you say about distributed timestamps?
I mean, so one of the as I mentioned before, we have a whole bunch of teams in London working on various static analysis stuff. And one of the things I've been encouraging them to think about is, given that Rust eliminates all of the low-level problems, I want to unlock their brilliance, and be able to apply static analysis at a higher level to Rust programs so that you can do things like write a TLA plus specification of what a distributed algorithm ought to do, and then be able to prove that your Rust code actually follows that specification, and if it doesn't, how they differ.
But TLA Plus really emphasizes how exploding exponentially the state space is for anything that's not causally related. So the question is, how can Rust help distributed systems programmers understand the ordering events in a distributed system when they try to use distributed timestamps, which are obviously not possible in special relativity?
So I think Rust has notational advantages over other languages for being able to express properties of your distributed protocol or whatever, but ultimately it doesn't have any intrinsic way of solving that.
Thank you. That's a very smart answer. What I'm looking at is there some way that we can extend Rust's borrowing and ownership to distributed systems?
I'm not going to come up with anything substantial here.
I apologize for the curveball, but I hope that it stimulates the audience.
Hello.
So you mentioned that you work for like smaller like startups before Facebook. So if you want to sell Rust to like a smaller organization or startup, like would you approach it in the same way, or are there other cases that you can make?
So in a small company, the cost of an individual person is much higher, relatively speaking. And so at Facebook, if someone spends 6 months working on a particular problem and it takes them 6 months to do it and they succeed, then they will get a good performance rating and they will have done the thing, and that person being out for 6 months will be a bit of a cost, but it's bearable. In a 5-person startup, having 20% of your people out trying to solve a problem for 6 months is huge. Like, that problem had better be getting your next round of funding, or, you know, breaking even or something like that. And so the previous company I was at, we were doing a distributed file system in pure C. It was in user mode, but it was very low-level user mode. It was a fuse file system. And we nominally had a quarterly shipping cycle. So what would happen is every 3 months we go, well, I guess it's about time to do another release. And it's like, oh, there's a lot of memory leaks. Let's fix up all the memory leaks. Oh, now it's crashing a lot. There's all these use after freeze. Oh, and there's deadlocking a bit too. And then there's this data corruption. And then 6 months into our 3-month release cycle, we'd finally have something we could get out the door. And then we'd start over again. And so that was the time when I discovered Rust. And I couldn't make the case saying, let's rewrite entire code base in Rust because it would solve this problem. Because we were running out of money in 3 months, and we had to get funding, and we couldn't get funding if we were in the middle of an enormous rewrite, and no investors would give money. And so I think starting at the beginning, like, well, let's have used Rust 3 years ago, is one argument you could make, but it's pretty hard to implement. But these days, you could probably, you could probably make the case in a new startup saying, let's just start with Rust. Like, this is the kind of problem domain that we're working in, whatever it is. Rust is not obviously completely mismatched with it, and it's going to give us some benefit. Certainly if the alternative is C.
You mentioned that there are still some code dumps when adopting Rust.
Yep.
But most of the time is FFI and other stuff. Recently, there are some security issue caused by unsafe Rust. So how does Facebook review the unsafe code or do some statistical analysis to like eliminate this issue?
Yeah, I'd love to have that, but we don't. We don't. I mean, the amount of unsafe code that turns up is very small. Like, it really is just around FFI things. I don't think we have any very few, maybe one or two places where unsafe is used in a way that's trying to do something that is not purely related to talking to another language. I would like to improve that area though. Like I would like our code review tool to flag diffs that use the unsafe keyword extra loudly, and like maybe have a policy of 2 reviewers or something like that have to sign off. And I would love to get sanitizers working across languages between C++ and Rust. And also I'd like our static analysis tools to understand across languages. And those are things that are not complete pipe dreams, but I'm not making a huge amount of progress on them yet.
Okay.
All right, so that's going to be all the time we have for questions today. Give another big round of applause for Jeremy. Like he said, he's going to be giving this talk again at RustConf next week. So if you're going to be at RustConf, we'll see you in Portland. We have this room until 9, so feel free to mingle for the next few minutes. Please take some pizza or some beer for the road. We need to get rid of all of it. There is way too much. Thank you so much for coming, everyone.